Welcome to Lecture 4.1, Binary Relations on a Set. To motivate the topic of this lecture, we know what it means for one number to be less than or equal to another, and we know what it means for two numbers to be equal. In this lecture, we will generalize these concepts to other sets. We will do this by defining the notion of a binary relation on a set. Though there are many types of binary relations, there are two special cases which we will see over and over again. First, there are the so-called partial orders, which are often written with symbols that you might recognize, like less than or equal to, or a subset containment, or maybe a squiggly version of the less than or equal to. And then the other type are the so-called equivalence relations, which are often written with symbols you've probably seen around, like a triple equal sign, or a congruence relation, which is an equals with a little squiggly on top, or just a squiggly in itself. As is often the case, the formal mathematical definitions are quite abstract and potentially unmotivated if we don't first see some visual examples to guide us as to why we are doing this and where we might be going. Okay, let's get started. Consider the set of all length 3 binary vectors, or if you prefer, strings. They're easier to write without parentheses and commas. Let's define what it means for one of these strings to be less than another one. Now, there's many ways we can do this. We could say that one string is less than another if it has fewer ones in it than the other, or we could put them in lexicographical or alphabetical order. But I'm going to say that instead that a string A1, A2, A3 is less than or equal to B1, B2, B3 if and only if each AI is less than or equal to the corresponding BI for all I. So for example, 001 is less than 011 and less than 101, but it's not comparable to 110. Because the initial 0 is less than the initial 1 here, but the final 1 is bigger than the final bit here, which is 0. So we can actually visualize this with something called a Hasse diagram. We will formalize and study this more later. And basically what we're doing here is we are putting the smallest strings on the bottom, and then as we go up in the diagram, the strings get bigger. So we put an edge between two strings if one is smaller than the other, and there's nothing in between them. So often we put arrows on these edges so we can tell which direction we're going, but if we lay it out nicely like this where we're going from bottom to top, we don't need those arrows, so we can drop them like this. Okay, this is an example of a so-called partially ordered set. So as I said before, notice that some strings are incomparable, like 001 is not less than or greater than 110. And also, one string is less than another if there is a directed path or an upward path from one string. So 000 is smaller than everything because we can get to anything else via a directed path. Our second example is the set of partitions on a 4-element set, namely 1, 2, 3, and 4. So let's recall what a partition is. It is a collection of subsets of, in this case, 1, 2, 3, and 4. So for example, 1, 3, 4, and 2, and the subsets have to be disjoint, and every element has to be in one of them. So this is a little bit clunky to write, so we usually denote this with 1, 3, 4, and 2, and these subsets are called blocks. So this is just a shorthand notation. And a refinement, we say that a refinement of this is what we get if we further break up the blocks. So for example, 1, 3, and the order doesn't matter. So 1, 3, 2, 4 is a refinement of 1, 3, 4, and 2. So let's say that a partition is less than another partition if the first one is a refinement of the second one. So this first one, where we chop it up further, is going to be less than this one. So with the Hasse diagram, we have all possible partitions of 1, 2, 3, 4. In here, this is the one that has a single subset, and this is the one that has 4 singleton subsets. So for example, 1, 3, 4, and 2, there are 3 different refinements of this. Well, there's 1, 4, 2, 3, 1, 3, 2, and 4, and 1, 2, and 3, 4. Well, I guess there's another one where we break them all up here. So this is one way to see those partitions. This is just a different way to visualize the same thing. Instead of numbering the elements 1, 2, 3, 4, we just draw the 4 dots, and it should be clear as to visually what we mean by these diagrams in terms of what partitions they represent. So notice that like this partition is not comparable. This is 1, 2, 3, and 4 is not comparable to 1, 3, or 1, 2, and 3, 4. The 2 examples that we just saw are so-called partial orders, and now we will do another type of relation that is called an equivalence relation. For our first example, let's let S be the following set of graphs with vertex set 1, 2, 3, and 4. Obviously, this is not all of the graphs on 4 vertices, but it's just a collection of 8 that I had space for, and I don't need all of these to get this point across. So 2 graphs, G1 and G2, are said to be isomorphic if they have the same structure. And I'm not going to formally define that. We will do that probably later in the course. But we will denote this with this congruence relation. So G1, this equal sign with a little squiggly on top, G2. And so let's go over which of these are equivalent to each other and which ones are not. So this first graph, which is just a 4 cycle, 1, 2, 3, 4, it should be clear that that is not equivalent to anything else on this list. Similarly, this graph, which has no cycles, but it has 3 edges coming out of a single vertex, is not like any other graph on this list. Now this graph, this is a length 3 path, 1, 2, 3 to 4. That has the same structure as this graph, which is also a length 3 path, even though the vertices are labeled differently, 4, 1, 3, 2. We say that these 2 things are isomorphic. This graph is a 3 cycle with a spoke or an edge sticking out. That is not like anything else on this list. And then finally, I claim that these 3 graphs here all have the same structure. Namely, these are all what we get if we take the complete graph, which is the graph if we take 4 vertices and include all 6 possible edges, and then just remove one of those edges. So even though I've drawn these or laid them out differently, hopefully you can see that if I redraw this first one, let's redraw it in a triangular shape here. So this is 2, 3, 4, this is 1, that this thing has the same structure as these 2 things. Even though, again, the vertices are labeled differently, like this has a triangle 2, let me add that, 2, 1, 4. The next one has a triangle 2, 1, 4. The next one, actually, all of them have triangles 2, 1, 4, but let's see, what is different about them? So this has a triangle 2, 3, 4, and yeah, 2, 3, 4 is not a triangle in here or in here, but they are still isomorphic. So what we can do is we can say that these 3 are all equivalent to each other. These 2 are equivalent to each other. This one is only equivalent to itself, and well, the other 2 are only equivalent to themselves. So these groupings are what we call equivalence classes, and we will also define these, I think, in the next lecture and study them in more detail, but it shouldn't come as a surprise that if we declare what it means for 2 graphs to be equivalent or 2 anythings to be equivalent, we can look at the set of all things that are equivalent with a particular element, and this partitions our set into equivalence classes. Okay, so more on this later. Our next example comes from linear algebra. So I know at my university that is a prereq for this course, but it need not be in general. And if you have not taken a course in linear algebra prior to watching this lecture, that's okay. You can skip this example or see what you can get from it, and no harm done. So let's let M sub n of C be the set of n by n matrices where the coefficients are complex numbers. We say that 2 matrices, A and B, are similar if A equals P, B, P inverse for some matrix P. Now, in a basic linear algebra class, you will learn that similar matrices enjoy a lot of nice properties. For example, they have the same eigenvalues and therefore the same determinant and the same trace. In a more advanced class, you might learn that two matrices being similar actually means that they represent the same linear map or linear transformation, just with respect to a different basis. Okay, so once again, like we did with graphs, with matrices, if we have a matrix A, we can define the similarity class to be the set of all matrices B that are similar to A. Now we are ready to abstract the definition of a relation from the examples that we've seen. So let's let A and B be sets. A binary relation from A into B is any subset R of the Cartesian product A cross B. If A and B are the same, and this is usually the case, we say that R is a relation on A. So in our prior examples, similarity was a relation on the set of matrices. Isomorphism was a relation on a set of graphs. And refinement was a partial order type of relation on partitions. And we defined an ordering on the set of length 3 binary vectors. Here's a very basic example. Let A be the set 1, 2, and 3, and B be the set 4 and 5. Then R, the following set of 3 ordered pairs, is a relation. 1, 4, 2, 4, and 3, 5. So we read this as saying 1 is related to 4, 2 is related to 4, and 3 is related to 5. There are several common ways to express that A is related to B. One way is just from the definition. We say that the ordered pair, A and B, is in R. But sometimes it is more convenient to write A, R, B. Finally, we can define a symbol like this squiggly less than or equal to symbol for A less than or equal to B. Or if it's an equivalence type relation, we can say A is this little squiggly similarity symbol. Or we can do the triple equal sign or something like this. So sometimes one of these is more convenient than another. Like if we want to define the relation up here, it's just easier to say R is the set of 3 ordered pairs. It's not as natural to define a symbol like this and say this is the set of 3 pairs. You can, but usually we want to say, once we define this, we can now say, we say A is squiggly less than or equal to B if and only if A, comma B is in R. Most binary relations, but not all, that we will encounter are of the less than type or the equivalence type that we have seen before. So we will formalize these as partial orders and equivalence relations. Let me list some common less than relations. So on the set of integers, also works on the set of real numbers, or on the set of rationals or natural numbers. A less than or equal to B, that is a standard relation. Or we can look at the one where A is strictly less than B. On the power set of a fixed set S, the relation A is a subset of B. Or we can define another relation saying A is a proper subset of B. Those are both relations. On the positive integers, if A divides B, that's definitely a relation. It's a different relation than the less than or equal to relation above. And finally, on the set of partitions, we can define a relation by refinement, as we've seen. Here are some common equivalence relations. On the integers, or the real numbers, or really just on any set, A equals B. That's a trivial one. That's actually equals. A less trivial one is on the integers. You've probably seen modular arithmetic. You know what it means for A to be equivalent to B mod 12. It's like telling time. 1400 hours is the same as 2 o'clock. So if you want to actually formalize this, we can say that A is equivalent, I'll write this like this, sub 12 to B if and only if 12 divides B minus A. So in other words, if the difference of B and A is a multiple of 12. So that is one of these equivalence relations. We will study this in more detail in a later lecture. On the power set of a fixed set, one way we can define a relation is saying that two subsets are equivalent if and only if they have the same size. This is, of course, not the only type of relation. We could define this relation, subsets, or we could define equality as well. And finally, on the set of matrices, similarity is one of these equivalence type relations. So notice the differences between the less than relations and the so-called equivalence relations. These, in some sense, generalize less than or equal to, and these generalize equality. Before we can define partial orders and equivalence relations, we need a few more definitions. These are basic properties of binary relations. Throughout, a relation R is going to be on a set A, and we say that R is reflexive if everything in A is related to itself. We say that R is transitive if whenever A is related to B and B is related to C, then A is related to C. We say that R is symmetric if any time A is related to B, then B is related to A. Notice that by symmetry, that also implies that any time B is related to A, then A has to be related to B. And finally, R is antisymmetric if whenever A is related to B, B is not related to A, assuming that A and B are distinct. An equivalent way to characterize this is that if A is related to B and B is related to A, then A has to be equal to B. Let's now turn our attention back to some of the relations that we've seen and see how many of them satisfy the following properties. So let's start with reflexive. Our less than, or maybe I should say less than or equal to relations. Notice that I've omitted the strict less than and the strict containment. I claim that all of these are reflexive. A is less than or equal to A. A subset is contained in itself. A number divides itself. And every partition is a trivial refinement of itself. Same with these equivalence relations. A is equal to A. A is equivalent to A mod 12. Two subsets. Well, a subset has the same size as itself. And two matrices are obviously similar to each other. Just take P to be the identity matrix. So both of these are reflexive, and similarly, both of these are transitive. It's easy to see that if A is less than or equal to B, which is less than or equal to C, we get that A is less than or equal to C. Same argument for subset and containment. And same argument for division. If A divides B and B divides C, then A divides C, at least on the positive integers. We'll deal with the case when we have negative integers, possibly 0 as well. And same with refinement. That's transitive. Same with equivalence relations. If A is equal to B and B is equal to C, then A equals C. Similarly, if A and B are equivalent mod 12 and B and C are equivalent mod 12, so are A and C. And the same thing with this equivalence on the size of subsets, and the same thing with matrices. Similarity is transitive as well. Okay, what about symmetry? Clearly, none of these things are symmetric. If A is less than or equal to B, well, the opposite generally does not hold, but the equivalence relations are symmetric. And that's easy to see if A is equivalent to B mod 12, and then B is equivalent to A mod 12, and similar with similarity. Finally, antisymmetry. These are not antisymmetric, but the less than or equal to ones are. So if A and B are distinct, then A less than or equal to B means that B is not less than or equal to A. Same thing with subset containment, and the same thing with these things as well. So the takeaway message is that the less than or equal to relations are antisymmetric, and the equivalence relations are symmetric, but both of these are reflexive and transitive. Let's continue with some more examples, and let's determine whether the following relations are reflexive, transitive, symmetric, or antisymmetric. So I'm going to make a little bit of a table here. So let's do reflexive here, transitive, symmetric, and anti-symmetric. And then I'm going to make some horizontal lines just so we can keep track as to which is which. Okay, let's break these up like this. So we first come to just the less than or equal to relation on the real numbers. We've already been over this, that this is reflexive, transitive, and antisymmetric. And similarly, the subset relation is reflexive, transitive, and antisymmetric. And both of these have a related relation, strict less than and strict subset containment. And these things, it's not hard to see, are both transitive and antisymmetric, but they differ in that they are actually not reflexive, because A is not less than A. And similarly, a subset is not a proper subset of itself, because it is equal to itself. It is a subset, but it is not a proper subset. So these relations are actually called irreflexive, which is different than being not reflexive. We'll talk more about this later. But so these are technically not partial orders, but they come from partial orders in a natural way. Next, this equivalence mod n. This is this is one of those equivalence relations, so it is reflexive, transitive, and symmetric. And similarly, the similarity on n by n matrices is reflexive, transitive, and symmetric. And now we come to divisibility. So divisibility on the positive integers, it's not hard to see that this is reflexive. Everything divides itself. Transitive, if A divides B and B divides C, then A divides C. And antisymmetric. So if A divides B for positive integers, then B does not divide A, assuming A and B are different. So now let's add 0 and see how that changes. So first of all, what I'm going to do is I'm going to draw this using a directed graph, and I will formalize this on the next slide. But I think that the idea should be clear. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to draw an edge between A and B every time A is related to B. So in this case, if A divides B. So everything clearly divides itself, so we're going to just draw little loops like this. I don't really need to draw that. Often we omit these loops because they're understood. Oh, I mean, they're not always true, like for the less than, but if we have a relation like this that's reflexive, we don't often need to draw it. Now we know 1 divides everything, so we're going to draw edges from 1 to everything else. It's going to get messy here, but that's okay. We know that 2 divides 4, 2 divides 6, 2 divides 8, and so forth, and 3 divides 6, and 3 divides 9. So you can see this is antisymmetric because there's no edges there's no paths that start at a vertex and then go somewhere else and come back. But if we add a 0, let's see what happens then. So if we add a 0, let's do that over here. Now remember that everything, like 5 divides 0, because 0 is equal to something times 5, namely 0 times 5. But 0 does not divide 5 because you cannot write 5 as anything times 0. So perhaps surprisingly, everything divides into 0, so we have it backwards edges like this, but this still does not create any sort of cycle, a directed cycle. And I should say that it's not okay to write 0 divided by 0, but it is okay to say that 0 divides 0, or at least I'm going to say that. There's probably some books out there that are going to disagree with me, but I say that because 0 is definitely equal to something times 0, namely anything times 0 works. So because of that, there's a loop here, and this relation is going to be reflexive. So this relation is still reflexive, still transitive, and still antisymmetric. However, on the integers, we're going to lose one of these. Do you see which one? Well, it's still reflexive because everything divides itself. We still have transitivity, but we don't have antisymmetry because 5 is not equal to 5. Sorry, negative 5 is not equal to 5, but we have 5 divides negative 5, and we have negative 5 divides 5. So we no longer have antisymmetry. So we got to be careful. Sometimes a relation has one of these properties on some set, but not on a different set. Okay, we've been over similarity, and finally, this last relation, we can understand it by drawing this directed graph again. So let me do that. 1, 2, 3, 4, and I'm just going to draw these ordered pairs as directed edges. So start with 1, 1. That's going to be a loop like this. 1, 2 is an edge like this. 3, 3 and 3, 4. Let's keep going. So 3, 3 is a loop here. 3, 4 is a path. 4, 3 goes backwards, and 4, 4 is like this, and then that's it. So this is not going to be reflexive. So I'll continue this down here. This is not reflexive because we don't have a loop on 2, so 2 is not related to itself. It's not antisymmetric because 4 is related to 3 and 3 is related to 4. So that's not antisymmetric. Is it transitive? So what does transitive mean? So I'm going to go up in this corner again, and transitive, one way to think about it in terms of the path is that if the directed graph, if you have A and B, and if you have C, so anytime you have an edge A to B and then B to C, you have to have an edge from A to C. And similarly, not just like two paths. If we have a path from A to B to C to D, anytime you have a directed path, that means that A is related to D, which means you have to have a direct edge from A to D. And here you'd have to have one from B to D. So let's look at the directed graph and see, can we find any paths greater than 1 where there's no edge? So the paths greater than 1, well, start at 1, you follow the loop and then go to 2. Well, that doesn't do it because we have an edge from 1 to 2. And here, yeah, there are many paths. You can just keep going around this circle forever. But for any path you have, the corresponding edge is going to be there as well. So this is actually transitive. And finally, it's not symmetric because we have an edge from 1 to 2, but not from 2 to 1. Okay, so hopefully this is further evidence as for what is coming on the next slide, which is to define our two favorite types of relations, namely the partial orders, those that are reflexive, transitive, and antisymmetric, like this, and then the equivalence relations, those that are reflexive, transitive, and symmetric, like this one and this one. Here is that formal definition. A partial order on a set P is a relation that is reflexive, transitive, and antisymmetric. We often denote this as an ordered pair consisting of the set P and the relation, and we call P a poset for short. This is short for partially ordered set. An equivalence relation on a set A is a relation that is reflexive, transitive, and symmetric. As we did on the previous slide, we can always visualize a relation R on a finite set A with a directed graph. Now I say finite set because for some infinite sets, like the real numbers, there's just too many points. You just can't draw all of the arrows. In our directed graph, the vertex set is just our base set A, and we include a directed edge from A to B if A is related to B. Note that the digraph of a partial order, if you exclude self-loops, those are these little edges from a vertex to itself, will be acyclic. That means there are no directed cycles. So you never have anything like this. And the directed graph of an equivalence relation will be bidirected. And by that I mean anytime you have an edge from A to B, you have an edge back from B to A. So because of this, we often will write that for short with a double edge like this from A to B. Or if we know it's an equivalence relation, we just don't need arrowheads everywhere, and we often just write it as an undirected edge and assume that it is bidirected. I should be careful to say that sometimes when we have a partial order, as I showed you earlier in this lecture, and we understand that the elements are ordered, say, from bottom to top, we don't necessarily include the directed edges in the directed graph. And so, for example, remember that example with the binary strings? Let me do the ones of length 2, 0, 0, 1, 0, 0, 1, 1, 1. Something like this. It's understood that the edges are directed up, even if we don't draw them. Let's return to something that we saw a few slides ago. A relation R on a set A is irreflexive if every element A is not related to itself. Every partial order on P, which we can think of as less than or equal to, has a related irreflexive relation, which we can think of as strictly less than. So formally we can say that A is strictly less than B if and only if A is less than or equal to B and A is not equal to B. Let's make several more remarks. First of all, irreflexive and non-reflexive are very different concepts. So irreflexive just means that there are 0 self-loops. And by self-loops, I mean, remember something like this. There are none of those. And non-reflexive just means that there are less than n self-loops. And here I'm assuming that our set A, or P, has size n. So in terms of quantifiers, irreflexive means that there does not exist an element in A such that A, comma A is in R, or A is related to itself, whereas non-reflexive means there exists an A, little a in A, such that A, comma A is not in R, so A is not related to itself. Similarly, antisymmetry and non-symmetry are different concepts. So antisymmetry means that anytime you have an edge A to B, then there does not exist an edge from B to A. And then non-symmetry just says that there is at least one edge A to B, such that the backwards edge does not exist. There could certainly be other things, C and D. I didn't draw this very well, but you get the idea, that are bidirectional. So in terms of propositional logic, antisymmetry means that there does not exist an edge A, B, and B, A in R, both, where A and B are different. And non-symmetry says there exists some edge A and B in R such that B and A is not in R. So B is not related to R. And here we are assuming where A and B are different. So both of these different concepts, they look the same linguistically, but they mean very different things. The exercise that we just did with the reflexive and symmetric properties, we can do with other properties. In other words, to take the opposite of a property, look at the negation. For example, let's see what the opposite of transitivity is. So R is transitive by definition if for all A related to B and B related to C, if A is related to C. To see what non-transitive means, we can take the negation. R is non-transitive means that this property is false. So it is not true that for all A and B and C in R, that A and C has to be in R. Remember how to do this? So the negation comes inside, and this for all flips to there exists, and it negates this inner clause. So we have there exists an A and a B, A related to B and B related to C, such that A is not related to C. So going back up here, being non this property, or non that property, is a little bit different than these modified properties that sound like they could be the same, but are not. I want to conclude this lecture by generalizing the notion of a binary relation to an N-ary relation. So if we have n sets, A1 up to AN, then an N-ary relation is any subset of the Cartesian product of these sets. Clearly, binary relations are the special case when n equals 2. And for binary relations, usually A1 and A2 are the same, but for N-ary relations, where they arise, often these things end up being different. And they do arise in database management systems. For example, suppose that a hospital keeps a database of its patients stored in a table with 4 entries. A1 is the patient ID, which is, suppose, a positive integer. A2 is the patient names, for say first name and last name, which is a string of characters. Suppose A3 maybe is the date that they arrived, which is a string of positive integers, if it's in month, month, day, day, year, 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 year format. And A4 is maybe the reason for emergency room admission, which is a string. This is a 4-ary relation on the Cartesian product of these 4 sets, defined as follows. So A1, A2, A3, A4 is an R, if and only if a patient with ID number A1 and name A2 was admitted on date A3 for the reason A4. Now here we can't really say just A1 is related to A2. We really have to say that this ordered 4-tuple is in R. As an example, consider a database R which contains the following 4-tuples. So the first patient is ID number 120423, name Alice Smith, date, was that January 30, 2018, for the flu. Next is, I'll skip saying the name, John Doe, who came February 9th, the same year, for a broken leg. Then there's Alan Johnson, who arrived in August for chest pains. Then there's ID number 042185, Catherine Greenman, who arrived on November 20th, 2018, for a pregnancy. And then suppose there's Maeve O'Neill, who arrived on the same date for, let's say, appendicitis. In the database language, SQL, sometimes pronounced SQL, the results of a query like this: select patient ID number, name from R, where admission date equals 11/20/2018 would be the following. So it's going to go up here and it's going to look at, so it's going to say select the patient IDs and the names from this table for all the entries where the admission date is November 20, 2018. And so here are those two entries. It literally just picks out the ID and the names. Mathematically, all we are doing is by intersecting the Cartesian product A1 cross A2 cross 11/20/2018, that's this date that we were looking for, with all of these elements in R. And then we are projecting onto the first two coordinates. So it's maybe not what you expected, but that is an example of an N-ary relation for n bigger than 2. They are hard to come by. There are some ternary relations, that's n equals 3, that occur in the mathematical field of Lie algebras. But most of the time, what we get are binary relations. They are the most natural. So in the next few lectures, we will study equivalence classes in more detail and then partial orders in more detail. Stay with us.